So this is lecture 13. And so what we're going to do today is we're going to start looking at chapter 5. This is arithmetic functions. Now, not surprisingly, we've already seen a lot of these functions before. So probably the best way to view this is when you think of numbers, what are the building blocks of numbers? These would be the prime numbers. And so when we're studying prime numbers and other things in number theory, it's helpful to have a class of functions. One of these functions we've already seen before. We've seen the Euler-Totient function. And so today we'll do the more general case of, what is phi of m for arbitrary m. One of the functions they also introduced today is the Mobius function. And they use this to talk about roots of a very special polynomial. This is an extremely important polynomial in a lot of algebraic number theory. I'm not going to do too much of that. If you want, that's something you can read. We have a huge number of topics we could look at. We've just finished our unit on cryptography, and interestingly today, I believe the colloquium at 1 p.m. in Bronfman 106 is going to be on n-true encryption. This is a completely different method of encryption than RSA. It uses lattices, and it's believed to be, I think, better security against quantum computer attacks. So if you're interested in cryptography, I would strongly recommend you go to the colloquium at 1 o'clock today. There will also be the infamous Lec13 debate tonight at 8. Professor Morrison from the Math Stats department will be taking the correct side in the debate. OK, so let's do the Mobius function. And I think you can put 2 dots on the O. I believe that's how you're supposed to do it. So we define mu of n as follows. It's 1 if n equals 1. It's negative 1 to the r if n is p1, pr distinct primes, and 0 otherwise. So for example, what would mu of 12 be? It would be 0, but mu of 10 would be 1, because 10 is 2 times 5. And then mu of 5 would just be minus 1. So the question is, why would we care about a function like this? So whenever your number has a divisor that's a square other than 1, so a non-trivial square divisor, this will be 0. And then if you are a product of distinct primes, it's negative 1 to the r. The way you can view 1 is it's a product of 0 primes. And so this kind of makes sense as to the natural definition. So why would we care about the Mobius function? So let me give you an example, and this is not in the book, as to why we care about the Mobius function. What's the most important function to study the primes? Riemann zeta function. So the Riemann zeta function, zeta of s, is the sum n goes from 1 to infinity of 1 over n to the s, and it's the same as the product over primes of 1 minus 1 over p to the s inverse. At least if the real part of s is greater than 1. So we have an infinite product of reciprocals. Rather than looking at an infinite product of reciprocals, what might be easier to look at? Yeah. So one thing is we could take the log, and the log of a product would be the sum of the logs. And there's a lot of things where we would do that. Has anybody here taken complex analysis? In complex analysis, you actually look at the logarithmic derivative all the time. And so that would be, the logarithmic derivative would give you like a zeta prime over zeta. Because the log of zeta, take the derivative of log of zeta, it's 1 over zeta, zeta prime. Turns out logarithmic derivatives are extremely useful. And because you have a product here, the logarithmic derivative becomes a nice sum. It turns out it's very tractable. So it's a good thing to look at, but for what we're doing today, not as useful. If you could get rid of one thing in this expression, what would you get rid of? I'm sorry?
I don't know how you call that, but multiply.
Oh, the product?
Yeah.
Well, so we can't, we need to keep all these primes. So instead of taking the product of the reciprocals,
I would
Oh, without the 1 minus? Yeah. Yes, we could get rid of the 1 minus, and then the reciprocals would just then be the product of all p to the s's. But of course, the danger is if we just had the product of 1 over p to the s inverse, that's the product of p to the s, that's going to just blow up. So we need something that will be nice. And so, I mean, it's essentially the same thing, but I could look at 1 over zeta of s. And that will just be the product over primes of 1 minus 1 over p to the s. So let's see what we would get. We would get 1 minus 1 over 2 to the s, 1 minus 1 over 3 to the s, 1 minus 1 over 5 to the s, 1 minus 1 over 7 to the s, dot, dot, dot. And then the question is, how do you deal with an infinite product? The best way is to make it a finite product. Take all the primes up to some point, see what you get, and then take the limit. So maybe what we'll do is we'll call this zeta of x, and it'll be the product of all primes going up to x. And so we'll stop at a certain prime, 1 minus maybe 1 over px to the s. So we can multiply this all out. And it's going to be a sum, right? So it'll be a sum of, say, an over n to the s. What's the largest n we could get? Yeah, 2 times 3 all the way up to the x prime, or the largest prime at most x. So it's going to equal a sum like this. Let's see if we can figure out what the an's are. What's a1 going to be? What's the only way when we expand this we can get a 1 for the denominator? Not s is 0, because s is just our variable. So when I multiply everything out for each term, I either take the 1 or I take the negative 1 over a prime to the s. If I want to have my denominator n to be 1, I've got to take 1 every single time. So what will a1 equal? I'm sorry? Not n to the s. I'm saying a1. So when n equals 1, I've taken 1 every single time. So when n equals 1, a1 is just 1.
Where do you get the denominator if you multiply 1 every 2?
You can write this as 1 over 1 to the s if you want, right? 1 to the s is just 1.
Oh, so my n to the s. Okay.
So when n equals 1, I have a 1 to the s, I have a 1 as my denominator. The only way I can get a term that has 1 as a denominator is to take 1 every single time. If I chose the 3 to the s, the 1 over 3 to the s, then my denominator would be a multiple of 3. All right? Building on our remarkable success with a1, let's go up and do a2. So how could we get a 2 to the s? There's only one way we can do it. We'd have to take this term and then take 1 every other time. So what is the coefficient of a2?
2 to the s.
Not 2 to the s. So when I take n equals 2, I have a 2 to the s down below, minus 1. Right? Because the only way I get a 2 to the s is I take the negative 1 over 2 to the s, and I take 1 every other time.
Oh, I see.
Right. How about a3? So I want now 3 to the s down below. The only way that's going to happen is I take this term, the negative 1 over 3 to the s, and I take 1 every other time. So what does a3 equal? Minus 1. Oh, it looks like maybe everything is minus 1 after a1. Yeah, the Riemann zeta function was all 1s. All right, let's take a4. So I want 4 to the s. How would I get 4 to the s as a denominator? Can't do it. It's 0. All right. a5. Any thoughts on what a5 would be? Negative 1. a6. What would a6 be? 1. The only way I can get 6 is I have to have 2 times 3. So negative 1 over 2 to the s times negative 1 over 3 to the s is going to give us 1 over 6 to the s. So A6 is 1. A7 is minus 1. A8 is 0. A9 is 0. A10 would be 1. And in general, an is just mu of n. So this is one of the reasons why the Mobius function is so useful, is 1 over zeta of x. So 1 over zeta of s is actually just the sum, and it goes from 1 to infinity, of mu n over n to the s. If we want to look at the reciprocal of the zeta function, here's where mu comes in. So hopefully this gives you an idea that the Mobius function is useful. One of the big themes of this class is trying to make conjectures. The biggest conjecture has to deal with the error term in counting primes. We know that the number of primes up to x is about x over log x, and we want to know what the error is. And it turns out it's related to where the complex zeros are of this function. And what people conjectured was, if you sum the Mobius function, that would be a way to attack what's going on. And it doesn't seem so surprising that it should be related, because the Mobius function is coming in with the reciprocal of the zeta function, so that maybe they should know each other. So I will post something online about this. But the Merton's conjecture was that if you sum n less than or equal to x of mu of n, that this is less than or equal to square root of x. And I believe, if true, I think this implies the Riemann hypothesis. But it doesn't go both ways. And in fact, it turns out that this conjecture is false. It took a while, but people were finally able to show that it's not always as small as you would expect. If you think about what's going on, you have a bunch of plus ones and minus ones, and a bunch of zeros. And you might expect there to be a lot of cancellation. So if you've taken probability, you might think central limit theorem. I might think things should be on the order of square root of x. You could replace this with a constant in front of here, and I believe we've now shown that that constant can get arbitrarily large, that there's some real x growth here. So this is far afield, but I wanted to give you a sense of where things lead to. This Mobius function is quite important. And so it has a lot of very nice properties. So let's consider the sum of d divides n of mu of d. What's the easiest d to study? Sorry, yes. What's the easiest n to study? If you had to choose an n, what n would make this work as easy as possible? I'm sorry? Prime, I think there's something a little bit easier than prime, but a prime is not too bad. 1. So if n equals 1, then you have the sum of d divides 1 of mu of d. That's just mu of 1, so it's 1. All right. If n is a prime, then we have the sum d divides the prime of mu of d. So what would this be if d is a prime? If n is a prime? What would my sum be in this case? Yes. So is the prime the only number that divides the prime? So it's mu of 1 plus mu of p. But we know mu of p is negative 1. So this sum would just be 0. All right. What's the next easiest thing to choose? So this is where things, we can now have a real fight. All right. Who wants to choose p1 times p2 for two distinct primes? Okay. All right, so we've got 4 people. Interestingly, more towards the back. Okay. What do other people want to do? P squared, the same prime, or more generally, p to the k. I think I'd rather do p to the k. And given that I have the chalk, I can, exert the power of being the teacher. So why is it better to do p to the k? It's exactly really the same as this. Because the only primes that divide it, it's going to be now 1p, p squared, p cubed. But I don't care about p squared, p cubed, etc. So the sum of d divides p to the k of mu d is equal to 0 if k is greater than or equal to 1. So it's very easy to get the prime powers. Okay, so now we can look at what happens if we have two distinct primes. For k? Yeah.
Because 1 is 0. Okay.
Right. And it'll still be 0. So if k equals 1, it reduces to what we had just done a moment ago. So just to write it as a nice closed form expression, we can do it like that. Okay, so now we could look at n equals p times q distinct. And now we would have a sum d divides pq of mu of d. All right, so what do I have to add now? So mu of 1, mu of p, mu of q, and mu of pq. So this would be 1 minus 1 minus 1 plus 1 is 0. Okay, making progress. What should we do after PQ? Yes.
Maybe like n, where n is the n times p, where p is not factor n. Or do we not jump that?
I don't think I'd go there next. And again, I'm not saying that that choice is wrong. Yes.
P to the k cube?
Yeah, or actually more generally, I would probably do n is p to the k, q to the l. L is a fun letter to write. And I would say, k and l are greater than or equal to 1. Because this argument would hold again. The only factors I need to worry about are the ones that are square free. And then also 1, but it's annoying, is 1 square free? Does any square divide 1? Yes, 1 divides 1. So you have to be a little bit careful with how you refer to 1. So when we do this, we'll also see that this sum is equal to 0. So it looks like the sum is equal to 1 if n equals 1 and 0 otherwise. So we'll change the consider to a conjecture, or maybe even better yet, let's say it as a lemma. So this is equal to 1 if n equals 1, 0 otherwise. All right, so we've done a lot of cases to get some intuition. So proof. Without loss of generality, what can we assume about n? Yes?
N is a product of some number of primes.
Okay, be a little bit more specific. Every number is a product of some number of primes. 12 is a product of primes. Do I want to consider a number like 12? Yes?
It's square free.
N is square free. Or 1. So we'll say it's a product of distinct primes. Because if there's ever a prime squared or prime cubed that divides, when I'm looking at the sum over d's, if d has a square factor that's other than 1, it's going to just be 0. So without loss of generality, I can assume my n has this form. And now we start doing the analysis. So we want the sum d divides n of mu d. So we're going to break this up into... Anybody know what class that is?
It's 1
It's 130? Okay. So we will break this up into numbers that divide n. So what's the simplest number that would divide n? 1. So I'm going to write it in different levels. So this is mu1. Now, what should my next level of numbers be? Each prime. So then we would get plus mu p1 plus mu pr. What's next?
P1, P2.
Good. So now it's products of two primes, p1, p2, plus mu p r minus 1 pr. All the way down to p1, p2, pr. Okay, so we've got a bunch of rows. This row is going to be, every term is going to be 1, every term will be negative 1, every term will be 1, every term will be negative 1. They'll alternate. Right? Okay, so we can now piece everything together. So the rows alternate. And so we get that our sum is equal to 1. Now, how many times do we have a prime? How many primes are there?
P choose 1.
Sorry?
P choose 1.
Not p choose 1, you're using the wrong letter.
Oh, R.
R choose 1. Right? We have r primes, we're choosing one of them. How many ways can we choose two primes, two distinct primes? It's r choose 2. So it'll be r choose 2 times 1. And then how many ways can we choose 3 primes? It'll be r choose 3. And then it'll be negative 1 plus dot 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 plus r choose r negative 1 to the r. So notice when I was writing, the product of primes, p1, p2, I assumed the primes were distinct. Because if I ever chose the same prime twice, it would just contribute 0. So there's a lot more terms than the ones I'm showing, but they're not going to matter. So what we get is this is the same as 1 minus 1 to the r. If you expand this using the binomial theorem, and so what's 1 minus 1 to the r? It's just 0. So this is the binomial theorem. So really, what we want to do is we want to write this as this plus 1 here is r choose 0. And then this is going to be negative 1, 1, negative 1. We can write this out a little bit more painfully as maybe this is negative 1 cubed 1 to the r minus 3. And if we write it like that, you can see the binomial theorem. And this one would really be negative 1 to the first, 1 to the r minus 1. This would be 1 to the r. So why is this important? What we have here is we really have a detector function. If I sum over all d that divide n of mu of d, I can detect whether or not my number n is equal to 1. Does this seem like a useful thing? Can anybody give me another way to tell if a number is 1? Yes? Look at it. Right? Doesn't this seem like ridiculous overkill? The problem is when you're doing things in number theory, you may not know that you're working with 1. You may have something given by a bunch of expressions. And so to be able to execute sums like this is quite important. So this allows us to detect 1. If you remember when we did the lecture on motivating quadratic reciprocity, I talked about Dirichlet characters. And we talked about primes in arithmetic progression, being able to detect, primes can go into A mod B. It's very useful to have detectors. So there's an algebraic result, which I'm not going to prove, but I will state. And then this may remind people who've taken probability of something. So this is the Mobius inversion formula. Let me I want to make sure I use the same notation in the book. So they'll define G of n to be the sum of d dividing n of f of d. All right, so I have some nice function f, and I get a new function g. Then f of n is the sum of d dividing n mu of d over n f of d, oh sorry, g of d. No, it should be mu of n over d. Because I know the comment I want to make from probability. So what this is telling us is that if I have a pair of functions f and g, if I give you f, is it easy to find g? Yeah, just execute the sum. What if I know g? Can I deduce what f is? Yes, there's a way to come out. All right, so the proof is algebra. So the proof is in the book, so I'm going to not go through the algebra. You can look at the algebra if you're interested. It's basically, changing summations and playing around with things. Does this remind you of anything? And if you haven't taken probability, you may not recognize this, but if you've taken probability, does this remind you of anything? Yes?
Bayes rule?
Okay, how does this look like Bayes' rule?
This is like G of D and then D in the denominator. That's a different thing. I'm kind of stretching a little.
Yeah, no, I'm saying this was not the answer I wanted, but we're trained as professors to say that everything is a good answer, and this is an interesting approach. Is that when we're doing things, we have P of A given B times the probability of B. So if you want to look at this in terms of Bayes, the probability of A given B times the probability of B, it definitely has something similar to that. And then in Bayes, you often have maybe BI, and you'd have a BI, and then you would have a sum over I. And so structurally, there will be some similarities between this and Bayes. So not the answer I was going for, but it's a justifiable answer. But there is something from probability that this kind of looks like. So I know at least 3 or 4 of you have taken probability with me. Where have we seen something like this?
The statistician.
I'm sorry?
The statistician stuff.
No.
Yeah, it looks like the binomial.
Not really binomial. So if I had it as A of say n minus d, b of d.
Oh, it's like convolution?
Yeah, so this is one of the things I love. Depending on how you write things, you can clue your students in or confuse them. And so if I write it like this, this is a convolution. And so rather than doing the algebra, I thought I would show you why we care so much about an identity like this. So this is also a good way to just introduce you to a little bit of probability. And so I'm not going to justify everything rigorously, but probability. So your density is greater than or equal to 0, and it sums to 1. It means you have to assign the probability everywhere. So we can have discrete probabilities, we can have continuous. If we do continuous, let's say I have a variable x with the density f of x, and another variable y with the density f of y. I could look at x plus y, and it should have some density f of x plus y. And the question is, what would that be? And it turns out that the density f of x plus y of, say, u would be the integral from minus infinity to infinity of fx of t f y of u minus t dt. Why would this be true? If I want x plus y to add up to u, if x equals t, then y has to be u minus t. And this is essentially the probability that that happens, and then I just integrate over everything. So this is called a convolution. And so if you take a probability course, this is extremely useful. If you take statistics courses, extremely useful. It allows you to understand combinations of random variables in terms of simpler ones. So now, why does that look somewhat similar? Well, instead of having maybe t and u minus t, I now have n over d and d. And maybe I'm doing things multiplicatively rather than additively. And so here, I'm talking about what is the density if I add two random variables. You could also talk about the density if you multiply two random variables. And that would be more something like this. I don't want to go into the technicalities. This is not a probability course. But what I'm hoping you see is that this looks a little bit like the convolution. So we can introduce an arithmetic convolution. And I believe it's often called Dirichlet convolution. So we'll say f star g of n is the sum d divides n of of f of d over, n over d times g of d. So part of this class is I want you to be put on the spot and see things that you have not prepared. What questions would you like to ask about this star operation? Yeah.
Is f star g equal g star f?
Yeah, so one is, does f star g equal g star f? And the proof isn't too bad. Because n over d and d, that's a perfect pair. And I can flip the order. So with a little bit of work, you can show that this operation is commutative. What else might you ask? And the hint was I did ask how many of you have seen abstract algebra.
Does this make a group somehow?
Yeah, it does make a group. So the next thing is it associative? Is f star g star h equal to f star g star h? And with a little bit of work, you can show that's true. Then closure is not going to be too bad. So we have associativity. What else might you want? Yes. What would transitivity be here? Transitivity is normally when you compare things. So if x is less than y and y is less than z, then x is less than z. So I think this might be what you were thinking of in terms of combining three things.
Some sort of inverse?
Okay, is there some sort of inverse? But before inverse, yeah, we need to have an identity before we can talk about an inverse. Any thoughts as to what the identity might be? Yes.
Maybe a 1?
Okay, so one thing is if we take one, so
There would be, would it be mu?
so would mu be the identity?
I don't know mu either.
So for the identity, we would want something such that, f star g, g star f should just be f, right? So let's talk a little bit about searching for the identity. So I'll use ID for identity such that identity star f is f star identity is equal to f. Right? That's what the identity should be. It should leave my function unchanged. All right, well, what is this going to be? So identity star f of n is going to be the sum of d divides n of whatever my identity is of n over d times f of d. And we want this to equal f of n. Yes?
We can, because we only want basically, we only want the identity function to be 1 when you put in 0.
Mm-hmm.
And so we can just use the function that we had, like the one identifier function that we made earlier this class. That was like the sum of all mu of n's of less than a number.
Okay. So we had something involving the Mobius function where the sum of d divides n of Mobius was just 1 if n equals 1 and 0 otherwise.
I don't know if that function is a name.
Well, the problem is that will only give us 1.
You want to give us f when d is n.
I'm sorry?
It'd be nice if it gave us 1 when d was n and 0 otherwise.
Mm-hmm. But the problem is we get to keep changing what n is. Right?
So you just want it to, if n over, if the idea of 1 was 1 and everything else was 0, you only get a term out of your sum if d equals n, which means you get fn.
Okay, so we want identity of m to equal 1 if m equals 1 and 0 otherwise. So if we had something like that, which seems to make sense for an identity function, it's 1 if m equals 1 and 0 otherwise, then if we put that in here, if d equals n, we get 1 here, and then we would get f of n, and anything else, it would vanish. So this is the identity function. It's equal to 1 at 1 and 0 everywhere else. So this is the sum of d divides m of mu of d. So the Mobius function is related to this. And then you can start asking, are things invertible? What would it mean for a function to be invertible? And not all functions will be invertible. But you can talk, so it's not going to be, unfortunately, a full group, but it's going to have a lot of properties similar to what you would find in a group. And what this tells you is that maybe we can invert some functions. And if you look at what was going on for Dirichlet convolution, the Mobius inversion formula. So I'm going to just restate the Mobius inversion formula. So we defined g of n to be the sum of d divides n of f of d. And the Mobius inversion formula was f of n was the sum of d divides n mu of n over d g of d. This is mu star g. Right? We could actually write this, if we wanted to, as 1 times f of d. We have a function that's just always 1. And so we could actually write g as 1 star f. Because if I look at my definition, if I just take the function that's always 1, this is going to just be 1 star f. Is everybody comfortable that G would be just 1 star f. Does that sound? Everybody's good with this? I'm just putting in a 1 over here every time. It really should be 1 evaluated at n over d, but if I always return 1, it's always 1. So f is mu star g, g is 1 star f, therefore f would be mu star 1 star f. And if things are associative, so what should mu star 1 be? It should be the identity. Mu star 1 should be the identity. What do we have over here? I can put in a 1 over here, right? This is actually 1 star mu. Well, 1 star mu is the same as mu star 1. And this just shows how everything fits together. There really is a nice connection between all these different things. So you can use this to formally attack a lot of these problems. And so mu is actually acting as the inverse to the function that's identically 1. So the function that's identically 1 does have an inverse. Not every function will have an inverse. What do you think will prevent you from having an inverse? What could be a problem? I'm sorry? So if you're not 1-to-1, that's definitely going to, cause some trouble in having an inverse. What else? Because things are arithmetic, maybe there could be some issues if you're 0 at a point. That might have some trouble. So I don't want to go too deep, but I want to give you a sense of why we care about the Mobius function, where it's used, what it can attack. And you can see now all the stuff you're doing in abstract algebra, this is actually useful. Okay, so the algebra proof of this, I'm going to leave, for Mobius inversion, I'm going to leave. So it turns out the visitor is not able to join us on Friday. So on Friday, we'll do the Euler Totient function. But so I just want to say a few things right now. So the Totient function is, phi of n is the cardinality of z mod and z star. And we've already attacked this for a lot of choices of n. We've done it if n is a prime or the product of 2 primes. More generally, if n is p1 to the r1, pk to the rk, then phi of n is phi of p1 to the r1, phi of pk to the rk. This turns out to be p1 to the r1 minus p1 to the r1 minus 1, dot, 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 pk to the rk minus pk to the rk minus 1. Or another way of writing this is I can pull out the p1 to the r1 pk, and I'll get n times 1 over 1 minus 1 over p1, 1 minus 1 over p2, dot, 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 1 minus 1 over pk. So what's nice is this tells you, clearly phi of n is at most n. Well, that's reasonable because it's counting the number of numbers relatively prime to n. It should not be able to exceed n. We will prove this on Friday. And hopefully we all agree that this is something that's worth knowing. Z mod and z star, this is one of the most important groups we could look at. A really good question to ask is, what can you say about the average size of phi of n? So typically, we want to understand the average order of these functions. These functions are often extremely difficult to understand at specific values, because they're going to fluctuate. But the hope is that if you look at a lot of values together, you can make sense of it. So we want to look at average size. So maybe what we'll do is we'll let a of x be 1 over x, the sum n less than or equal to x of phi of n. And to be fair, we should probably take x to be an integer. So look at the first x values. And then this is a very natural question. How quickly do you think this function is growing? Can somebody give me a lower bound, and it can be a really crappy lower bound? Yes?
1.
Yeah. I mean, the really crappy lower bound is 0, but there's at least one number relatively prime to n. 1 counts. So phi of n is always at least 1. So we clearly have 1 is less than or equal to a of x. What about an upper bound? What would you say for the upper bound?
X is an easy one, right?
Why x? Each one of these is at most x,
Yeah.
right?
There's X of them.
And there's x of them, and we divide by x. So a really easy upper bound is x. We can do a little bit better than x. Each one of these is at most n. So we're summing from 1 to x. That's x plus 1 over 2, divided by x. So this should be at most x plus 1 over 2. A little bit better. There's a huge difference between 1 and x. What's the correct growth rate? So any numbers that are easy to analyze here? Primes. So for primes, it's just going to be n minus 1. If we knew how many primes there were, that could be useful. So if we use the primes, we would have basically a contribution of all the primes less than or equal to x of p minus 1. And then we would have to try to figure out what can we say about a sum like this. So it's large here. Frequently in something like this, a good thing to do is to break it up and say this is greater than or equal to the sum, x halves less than or equal to p less than or equal to x. Because now if my prime is at least x halves, this is going to be at least x halves minus 1. And the minus 1 doesn't really bother me that much. Because the problem is, if I go all the way from the beginning, it's such a large area, it's such a large interval, that the size can change greatly. But if I can confine myself to a smaller subinterval, now p goes between x halves and x, they're now all roughly the same size. So this is like a dyadic decomposition. And now I would just need some result about how many primes are there between x halves and x. And I should be able to get something like each one is giving me x halves, and the number of primes is going to be roughly x halves over the log of x halves. Then if I divide by x, I'm getting roughly x over 4 log x. So this should give a lower bound of roughly x over 4 log x halves. You have to do a little bit of work to make this careful, but what this is telling you now is this is really close to this. It's differing by a power of logarithm. So in terms of trying to get a sense of what's going on, by looking at numbers like this, we have a great deal of understanding. The difficulty is how small could phi of n be? Maybe another way to attack this is to look at when this is small. And so I'll let you ponder this for Friday. What's the smallest value phi of n over n can be? So try to figure out how small can phi of n over n be. Okay. So that's a good place to stop.